Okay, so last time we just looked at some historical stuff with gravity, looked at the geocentric model, the heliocentric model type stuff. We looked at Kepler's laws a little bit of historical review. A bunch of that was from grade 9 science. But today what we're going to do is we're going to start focusing a little bit more on Newtonian gravity and actually calculating gravity and that type of stuff. So there's different theories of gravity, but the main one that we're going to use was classified as Newtonian gravity, and it's a pretty simple type of idea. So when you look at what he did, there's different theories of how he actually came together. But what you often hear is Newton took his three laws, like three laws of motion and stuff like that, like your F equals ma inertia, that type of stuff, and he took Kepler's laws and he put those two together in order to get his theory of good old-fashioned gravity. So sort of like a combination of his three laws and Kepler's laws, put them together, and that is where his theory of gravity kicks in. Now, it's interesting because, again, with the stories that you hear from way back when, apparently there was no technical proof or documentation that he actually did this. So it's, again, that's just one of the stories that you hear when, especially in university and physics and stuff like that, you'll hear some of the historical stories, and there's apparently no real actual proof that he did it. That according to some people anyway. And this actually often kicks back to the other story that he stole a lot of the ideas from Robert Hooke of how gravity might work, and maybe that's why there is no actual proof. It's kind of hard to go with, though. I mean, Newton was an absolute genius. He did so much incredible stuff. So whether they found documentation or not, whatever. It's just, but it's an interesting story. So anyway, if we actually piece it together, if we sort of look at things that he actually looked at, first of all, the force of gravity depends on a lot of things, but one of the biggest things, obviously, is mass. And he realized that the force of gravity was directly proportional to mass. But the trick is, so to speak, is you can't just have one mass. You actually need two masses. A single mass by itself can't have a force of gravity. You have to have a source of gravity and the need to act on something else to actually have the force of gravity. It's sort of like if you're floating in space all by yourself, you can't apply a force to anything because there's nothing for you to push on. So you need two masses. You need a big mass and a small mass, two small masses, two big. Anyway, it doesn't make any difference, but you need two masses. One for the source of the gravity and then one for the gravity to actually act on. Now, of course, the thing is, when one force or one mass is applying gravity, so is the other one. So you need two masses, but they both actually have gravity, and it's a mutual force between the two. This is Newton's good old-fashioned third law. There's always two forces equal and opposite. So of course, like the Earth is pulling on you with gravity. Well, you're also pulling on the Earth with gravity, and of course the two forces would be equal to each other. So the masses, of course, is really, really important. He also figured out that the radius was really important. So the force of gravity is also connected to the radius. Now I'm just going to hold off a little bit on the proportionality statement here for a second. Think about it this way. Suppose you have, my favorite analogy for this, suppose you have a paintball, and you take that paintball and it's in the middle of a magical glass sphere, and what that paintball is going to do is that paintball is going to explode. Hey, my thing turned red. There we go. Suppose the paintball explodes and it coats the inside of the glass sphere reddish. Okay, no big deal. Now, what if you did the exact same thing, except you made the glass sphere twice as big? If you made the glass sphere twice as big, and you took the exact same paintball and you put it inside and it exploded, it would still coat the inside of the bigger glass sphere with paint, but the layer of paint would be thinner because it is a much bigger sphere. Now, if you make the radius twice as big, the layer of paint is not going to be twice as thin on the bigger one. It's actually going to be 4 times thinner. So the radius is twice as big, but the paint layer is going to be 4 times thinner because surface area of a sphere is 4 pi r squared. So every time you make the radius twice as big, since it's squared, the surface area becomes 4 times as big. So the same idea applies to gravity. As the gravitational field radiates out from the mass, it gets weaker and weaker and weaker and weaker. And since it's taking the shape of a sphere, as it radiates out from the object, it becomes very weak very quickly because the surface area that the gravitational field is spread over on is the shape of a sphere, just like the paintball idea. So we figured out that it was actually an inverse squared relationship. So as you get further and further and further and further away, the force of gravity gets weak exponentially as you move out, because it's going out in 3 dimensions, not just 1 or 2. Okay, so these two things sort of put together, they came together to make his general Newtonian gravity expression. So you take these two things, we can put them together, and the force of gravity is going to be directly proportional to not just one mass, but 2 masses. I like to do a capital M and a lowercase m. Some people do M1, M2, it doesn't make any difference. But the force of gravity is directly proportional to the product of the 2 masses divided by the radius squared. Now, of course, this isn't an equal sign over here because we are missing the constant. You can't have this as an equal sign until you have a constant. So you'd actually have to graph it out, and this is what we did in our intro section. If you do the FG versus M, you'll get a straight line. If you do the FG versus 1 over r squared, you'll also get a straight line. And your combination of all the slopes put together for the different variables gives you the constant. Now, it took a long time for them to actually find the constant. It was about 100 years later by a guy named Cavendish, apparently, who actually found the constant. But that is what's called the gravitational constant. And it has a value of 6.67 times 10 to the negative 11, which is a very crazy constant. And that's Newton meters squared per kilogram squared. So 6.67 times 10 to the negative 11 Newton meters squared per coulomb squared is the gravitational constant. And the symbol for that is a capital G. That's why for 9.81 you have to use a lowercase g, and for this one it's a capital G because they're two very different things. And that's how we can actually calculate the force of gravity. So if we sort of put together, force of gravity would be gmm over r squared. And this is the 6.67 to negative 11. Now, one of the tricky things, so to speak, that you got to be careful of is that radius. That radius is from between the centers of mass. So you have to go from the center of mass to center of mass for the radius. For space stuff, they're so far apart, the radius of the planet or the star or whatever it is usually doesn't make that much of a difference if they're really far separated. But for example, if you're going to calculate the force of gravity between like the space station and the Earth, that radius has to be to the core of the Earth, not to the surface of the planet. So it's a little bit different that way, but we're looking at that as well. So a lot of space calculations kick in with this, masses of planets, stars, moons, radii, that type of stuff. And this is where the sheet that you guys got last year in grade 11 has all your constant numbers and that type of stuff. Your super sheet from last year comes in really handy. It's the inside covers of your grade 12 textbook because the mass of the moon, the Earth, the sun, the radii of the orbits are all in there. Those values you guys are going to be using an awful lot. Just be really careful with any of the radii that are in there because often those radii are given in kilometers, and we will be calculating stuff using meters. You got to be a little bit careful with that. But that's a really important set of numbers and a really important sheet to have handy when we're doing actually this entire fields unit. We're going to use it a whole bunch, and then we can actually calculate some stuff. Okay, so let's just jump right in and do a simple calculation and sort of show how all this type of stuff actually works. Okay, so let's try this. Here we got a satellite above the Earth, and let's make something up here. Let's say we have a 1,200 kilogram satellite, and let's say it is 450 kilometers above the Earth. Okay, and we are going to find out what is the force of gravity between the two. Okay, it's just a really basic type of calculation, no big deal. So our basic expression, force of gravity, is gmm over r squared. I like to use capital M, little m. Some people use M1, M2, doesn't matter. I like to use my big M as my bigger object, and that's just what I like to do. So for me, this big M, this of course would be the Earth. So that is about 5.97 times 10 to the 24. You can find that mass on your super sheet or the inside cover of your book. And this right here would just be the 1,200 kilograms for my satellite. Now the radius, this is where you got to be careful, because that radius is not the 450. That's 450 above the Earth. That's 450 kilometers. So you have to change that into meters. So that radius is going to be the radius of the Earth plus 450,000 meters. So you got to be kind of careful with that radius. It's when things are really close together. Other than that, it's all just plug and chug. So you got the 6.67 times 10 to the negative 11. You got the mass of the Earth, mass of the satellite, and I recommend multiplying those out and pressing equals and getting the numerator for that, and then squaring the denominator and writing that down, and then dividing the two so there's no order of operation mix-ups with your calculators and that type of stuff, especially when you're first starting out these types of calculations. So if we do that, the numerator, we should get about 4.78 times 10 to the 17, and the denominator, put in the raised to the Earth, add that, press equals, square it, and we should get about 4.66 times 10 to the 13, and then we can divide those two out. And if we do that, we will get approximately 1.02 times 10 to the 4 newtons. So that would be the force of gravity between the two objects. So now let's do something similar for between the Earth and the Sun. So we got the Sun over here. We'll say that's the Sun. There's the Earth. And we're just going to find the force of gravity between the Earth and the Sun. So same type of thing. The force of gravity is going to be gmm over r squared. G is 6.67, negative 11. You got the mass of the Sun, which is 1.99 to the 30. You got the mass of the Earth, and divide by the radius squared. Now the radius listed on your sheet and in your textbooks of that should be from center of mass to center of mass. So we don't need to add anything to it, and even if we wanted to, the distance between these two is so great that the actual radii of the objects would be irrelevant. So we can just type in the G, the M, we multiply them out, and the radius between the two and square it, and everything should work out. Okay, so your numerator that you should get is around 7.92 times 10 to the 44, and then we'll divide that by the radius between the Earth and the Sun is 1.5 times 10 to the 11, and don't forget to square that. And then if we divide the two out, you should get around 3.5 times 10 to the 22 newtons. So objects really close to each other, we had to incorporate the radius of the planet when it's set above the surface or above Earth. Sometimes this gives it from the center of mass, but here, same type of calculation, except they're so far away the radii of the actual objects is irrelevant, and it's all just the measurements are given from center of mass to center of mass. For doing these calculations, make sure you know how to use your calculator. Make sure you're using the scientific notation button, like your double capital E button or your EXP button. If you're off by powers of 10 for every calculation, that's often the reason why you got to be careful that you're using your scientific notation properly in your calculator, and then the calculations should work out okay. But that's the basic way to calculate the force of gravity.